Sometimes we have circuits where we can't identify strictly series or parallel networks. And so they set up like this, where I have, again, a power supply, a battery. So here's an R1, we'll say a V1. We've got a second resistor. So far, so good. We set up another resistor, R3, and then all of a sudden there is an extra battery somewhere. Ooh, it's not a very good battery. That's our V2. And just for good measure, we'll put another resistor there. Okay. So we might think, in fact, that R2 and R3 are in parallel. They are not, because they do not have the same voltage. These two arms are in parallel with each other. Okay, so the voltage across this must be equal to the voltage across this. That's true, but these resistors are not in parallel with each other. This is not in series with this one. So we have a little bit of work to do to try to figure out if, in situations like this, which we'll run into occasionally, what is the current if we're given the voltages, or if we're given the current, what is the resistor, or what is the battery, or something like that. So to set this up, you need to set up, you're going to use current in equals current out, and the voltage around the loop is 0. And so the way we'll set this up, I'll do it in general, and then we'll do some specific problems as examples. But we can say, okay, I'm going to call this, say, current 1. And I just pick a direction. I don't actually know the direction of the current. It's going to depend on the values of these voltages. I might pick this as current 2 and this as current 3. And you might be tempted to then call this current 4. But if you notice, it's the same current coming into the battery and leaving the battery. So this is actually I1. This is the same current that comes into the battery and then leaves the battery. It just splits off. So if we look at current in equals current out at this junction, so we use this mostly at junctions. So if I do this at this junction, I get that I1 is equal to, so current in is equal to current out, which would be I2 plus I3. Those are the two currents going out. I can repeat this down at this junction, and it says current in is I2 plus I3 equals current out. So you could get something that says I2 plus I3 equals I1. But notice this is exactly the same equation that we have here. So it's not going to give us any new information. It's just true. It's good to check that it's true, but you don't need it. So I'm going to get rid of this. Then, so I've used this, and then what I need to do if I'm trying to find the current, so if R1 and all the voltages, if all the voltages and the resistors are given, for example, and I'm asked to find the current, I've got 3 currents, so I'm going to need 3 equations to solve for 3 unknowns. So this is my first equation, and then I need 2 more equations that are going to come from 2 loops. So I can do this any number of ways, but what I tend to do is pick some place at the bottom, like here, and then I think about walking around the circuit like this in a loop. So I could do the interior one, I could do the outside loop, I could do this loop. There are 3 possible loops I could do. So I could do the 2 insides and 1 outside, but I only need 2 of them. If I do all 3 of them, I'll get 2 equations that are exactly the same. Just like I got 2 equations that were the same doing these 2. So if I start with this loop, I'm going to do voltage around the loop. So I'm going to start here, go through everything, and then come back to this spot and say that my total voltage around this loop, so I'm going to call this loop 1. So I'm going to say the total voltage around loop 1 is going to equal 0. So I just need to add up the voltages. And at this point, it's going to be useful to hold on to some sign conventions. Okay, so I'm actually going to move this over here. Delta V is equal to 0. So this is the loop 1. Loop 1. So this is my first equation. My second equation is going to come from here. So my sign conventions are that if I go across a battery, if I walk across a battery, I run my loop across the battery from minus to plus, that's a positive increase. That's an increase in energy. Think of it as an elevator going up the hill, because I've gone from the minus side to the plus side, so that is a positive V1. So that's going to be V1 plus V1. So I've increased my energy. Now I'm starting to go through resistors. And so going through resistors, if I go in the direction that current flows, that's going to decrease my energy because my current flows this way, so I'm falling downhill. So that will be minus I1 R1. That's this hill. And then I do the same thing here, minus I2 R2. And then notice I'm now walking across this battery the wrong direction. Right? I'm going downhill, going against the direction the battery wants to go. And so this would be a minus V2. And all of these together equals 0. Okay? So our notes now on our conventions are that if we go across a battery in this direction, then my delta V is greater than 0. I've got a positive change in voltage. And if I go across a resistor, this is the direction of the current. So if we follow the current, so if we go across, if we walk across, I guess I should label my current in a different color. So that's my current, I1. And if I'm going through this resistor in this direction, then that means I'm decreasing my voltage. I'm spending that energy to heat up this resistor. Okay, and that gets me my sign convention. And again, we're saying V1, R1, R2, and V2 are all given in a problem. So we're looking for I1 and I2. So I have these two are unknowns. So I've got one equation. Now I have a second equation. There's my second equation. And now I need a third equation. And I can get that from either doing this outer loop, or I can get it from doing the inner loop. And I'm going to do the inner loop, just so we can watch the sign convention. So I'm going to start here, and I'm going to go like this. So this is loop 2. Okay, so loop 2. I still say the change in the voltage around loop 2 is equal to 0. I start down here. Now I'm going across this battery in the correct direction. I'm increasing my energy, so that's a positive V2. And now look at this, I'm going across this resistor in the wrong direction, right? The current is going down, at least the way I've labeled it. I could have been wrong, but I'm going across the resistor in the other direction. So that's going to be a positive, because I'm opposite this, positive I2 R2. And then I'm coming around, and notice now for this resistor, I'm going in what I think of as the normal direction, the way that it would be a decrease in potential energy. And so this is equal to 0. And this is my third equation. And then it's just a matter of reorganizing this to solve my system of 3 equations with 3 unknowns, where my currents are my unknowns. So I'll do this as an example with actual numbers. But I wanted you to see the setup, because all we're doing is using current in is equal to current out. The change in energy when I go all the way around the loop has got to be equal to 0. And these are the sign conventions. So you can use this in place of doing parallel and series resistors. This will work also. But in general, using series and parallel resistors is easier. In general, using series and parallel resistor networks is easier than having to solve a system like this. So I generally only resort to this when I can't identify things that are in series or in parallel.